9.6 Compositions of Reflections. This is our very last section. How exciting. All right, we know what compositions mean. That means we are going to have multiple things going on. And the main idea here is that if two figures in a plane are congruent, that means we have isometries, right? We have isometries, and which means we are doing either translations, reflections, rotations. Okay, so if two figures are isometries, you can map one onto the other using a composition of reflections. This is one of my favorite sentences in here. The theorems in this lesson lead to the facts stated above. Complete proofs of these theorems are beyond the scope of this course, which is just a reminder that we are just skimming the surface of geometry, but it's fun nonetheless. We will suggest approaches to the proofs of these theorems, but we aren't going to go into detail. But we know that because they are theorems, they are proven in some fashion. All right, let's start here. Take a look at our theorems. Theorem 9.1 says that a translation, right? That's where we just slide it. This is a slide. A translation or rotation, that's where we go about our center of rotation, right, is a composition of two reflections. And reflections are where we go from here and we flip and go across the line. Right? This is a flip. Now, 9.2, we were told, Theorem 9.2, these are converses of that. So let's take a look here. These are a little bit easier to understand. A composition of reflections across two parallel lines results in a translation. So if we reflect across two parallel lines, we end up with a slide. Well, let's look and see how this happens. All right, we have our two parallel lines here, and we have our pre-image. And how do we do a reflection? Remember, reflections are perpendicular. So we have our perpendicular lines. We just draw in our perpendicular lines. These are perpendicular. Both are parallel lines. And then we take this point and we measure this distance, and we know it's the same distance on the other side. And we mark our image point. And we do the same here. We mark our image point, and we know that these two are congruent. And then, okay, we do the same thing again. We take our image point and we flip it again. We have a perpendicular line here, and we flip it over here. And we know that this length is congruent to this length, and we do the same thing down here. Okay, so do you see how in all 3 points, we would do all 3 points, but that would get messy. Do you see how if we start here at 1 and go to 3, that it's just a slide, a translation? So we take this slide. A slide is made up of one flip and then two flips. Equals 2 flips. Because the first flip makes it opposite orientation, and then the second flip fixes that. Let's look at the next one. A composition of reflections across two intersecting lines is a rotation. So we get a turn, right? A turn equals 2 flips, but this time our lines are intersecting. And so we see here's our point of intersection, and you can see by the dashed line that's going to be our center of rotation, but we are not rotating this time. We have intersecting lines. Again, we are going to draw our perpendicular lines. I'll draw one up here, perpendicular lines, right? And then we measure this distance, and it equals this distance, and this distance equals this distance, and so on for all of our points. And we have our pre-image, and we turn it into our image. Okay, well, now we have opposite orientation, and so we need to flip it again. And so I'm going to draw a new set of perpendicular lines to my other line here, and then this length is going to be congruent to this length, and this length is going to be congruent to this length. And so you can see how that if we start at figure 1 here and we end up at figure 3, that we could have done that with our protractor, right, and our compass or our ruler, and come out of this point here, right, and rotated it around. But instead, we flipped it up here to figure 2 and flipped it again to end up at figure 3. So a rotation is 2 reflections across intersecting lines. A translation is 2 reflections across parallel lines. All right, let's take a look at our first example. We want to know what is the image of R reflected first across line L. So the first thing we do is go across line L, and then across line M. So 2 reflections. And then we are asked, what are the direction and distance of the resulting translation? Okay, well, the first thing we're going to do, we know that across 2 parallel lines is going to be just a slide, right? A translation. And the first one, we take our point, and we would do multiple points on our R here, and we use our perpendicular line, and we measure this distance, and we make it congruent, and we get our image point. Okay? And then we are going to take our image point, and we have another perpendicular line, and we flip it across there again, and we get our new image point. So how far have we moved? Well, this is kind of interesting. The distance between our 2 parallel lines is 1 plus 2 ticks, right? A to P prime and P to B prime. From here to here measures 1 plus 2. Because our distances are congruent across our line of reflection, I add another 1, right? Another 1 over here and another 2 over here. So we move a total distance of 2 AB. The distance from A to B, which is the distance between the parallel lines. So the distance a translation is twice the distance between your parallel lines. The distance of our translation equals 2 times the distance between our parallel lines. So that's kind of neat. All right. Problem 2 is theorem 2. Reflections across intersecting lines. We are told that lines L and M intersect at point C, so there's our center of rotation, and form an acute angle that measures 70 degrees. So we know our angle here is 70 degrees. What is the image of R reflected first across line L and then across line M? So 1 and then 2, we're going to go across L and then we're going to go across M. What are the center of rotation and the angle of rotation? All right, well, we've done this before. We have rotated around, but this time we are not doing a rotation. We are creating a rotation doing 2 reflections. So how do we do reflections? We draw a perpendicular line, right? And then we take our point P, and we know that these distances are congruent, and we end up with point P prime. And so we would do that for all of our points. Here, draw our perpendicular line, perpendicular. We know that these are congruent. I'm going to mark a congruent about there. Oh, to about there, right? And then I would do that for multiple points. So I am going to end up with something that looks like that. Right? This one kind of tilts in this way, so this one tilts in this way. And then I would do the same thing again. I'm going to take my new points here, and I'm going to draw my perpendicular lines. Right? I would do a couple of points. Theoretically, we should do all of our points. We know that our distances are congruent. 1, 2, 3, 4, 2, 3, 4 across our line of reflection here. This one's up kind of close. And that's that short one there. That one's up here. And that's that one. A little harder without a ruler. This one goes in here. And go here. So we end up now with, it's not quite my R that I started with, is it? You get the idea. This is why we use the proper tools. We use a ruler to measure things out. All right. Our protractor, get our 90-degree angles, our 90-degree, our perpendicular lines, proper tools. And we know that the intersection point would be our center of rotation. And you could see how R would, if the hand of a clock, would have spun around over here. We have created a rotation using 2 reflections. Now we want to know the center of rotation, and we know that we are rotating clockwise. We rotated clockwise about the intersection point. Therefore, our center of rotation is point C, and this is kind of fun here. We know if we were doing a rotation, we would measure this distance and this distance, right? As we rotate around, and we would make these 2 congruent. These distances are congruent here. What do you see? I see congruent triangles by side, side, and reflexive property side. We also have right triangles, so we could use HL. But if these triangles are congruent, then I know those two angles are congruent by CP/CTC. And then I can say that 3 and 4 are congruent. Angles 3 and 4 are congruent as well. What is the angle between our two lines here? Right? It's 1 plus 2, right? 2 and 3. And then on this side, we add another 1 angle, and on this side, we add another 2 angle. So these right here are 70. I know that 1 plus 2 equals 70. Our angle of rotation is going to be 140 degrees because, let's see, our angle, measure of our angle of rotation equals 2 times the measure of the angle between our lines. That looks an awful lot like what we just did with our parallel lines. All right, keeping this information in mind, pause the video, do the next problem. All right, that was a bit challenging. I hope you were using a ruler, because I didn't, and it was not a good idea. All right, right tool for the right job. Okay, even if you tried to freehand it, hopefully you realized that we reflect across the first line here, line A, and it makes opposite orientation. We do that using our perpendicular lines, and then we are going to reflect again across line B, and that flips the orientation back to the original. And all in all, this is just a rotation about point C. So our center of rotation is C because that is the intersection of our lines. And we know that the measure of the angle of rotation is twice our angle of our intersecting lines. So 2 times 45 is 90. All right. These are going to take a little bit of effort. They're not hard, but you're going to have to be a little careful. All right, we have a lot of words coming up here. Let's see if we can figure out what they all mean. In a plane, any two congruent figures with the same orientation, that means not a flip. It means we've either slid them or rotated them somewhere. So any two congruent figures with the same orientation are related by either a translation or a rotation. Therefore, by 2 reflections. Right? We can make a translation reflecting across 2 parallel lines, and rotation is a reflection across 2 intersecting lines. Suppose that 2 congruent plane figures have opposite orientations. So now we are looking at opposite orientations. That means that we have done more than just translate it and more than just rotate it. Okay, so we have opposite orientations. If we reflect A to get A prime, that has the same orientation as B. Thus, B is a translation or rotation of image A prime. Well, how did we get to A prime? We either did 2 reflections across parallel lines or 2 reflections across intersecting lines, and then we either translate or rotate again to map A prime to B. So the net result is that 3 reflections are used to get figures with opposite orientation. This is what the fundamental theorem of isometries is saying. It says that in a plane, one of 2 congruent figures can be mapped onto the other by a composition of at most 3 reflections. So we know they're congruent, so they're isometries, but if they have opposite orientations, it's going to take more than either just a translation or a rotation. We will need to do another reflection. Okay, so if 2 figures are congruent, let's look at our problem. We have 2 figures that are congruent and have opposite orientations, but are not simply reflections, right? We can reflect to get opposite orientation, but we can't say that you can't just do a simple reflection. Then they are a translation and a reflection that will map one onto the other. This is called a glide reflection. Translation is the glide, and reflection across a line parallel to the direction of translation. So let's look at our paw print here. This is paw print number 1. Shouldn't cover up the only part that they have that lets us show orientation. Here's paw print number 1. Now, how do I get up here to my final paw print number 3? Let's call these A and B, because that's what they called them in our lots of words up there. So we have paw print A, and we want to get it to paw print B. We notice that they have opposite orientation, but I can't simply reflect across this line here. There's no way to just do a simple reflection. So I need to first do a translation to get A prime, and then I'm going to reflect to get B. Right? Do you see our glide reflection? Now we also could have reflected first and then glided. Okay, that would still be a glide reflection. Doesn't matter which order you do it, you end up in the same spot. Results in our opposite orientation. So let's look at our example problem here. How do we find a glide reflection image? All right, we want to know what is the image of triangle TEX here for a glide reflection where we have our translation rule and the line of reflection is x equals 0, right? Remember our translation rules tells us how far to move x and y, and then our line of reflection tells us what we are flipping across, how far away from that line we are flipping across. So in the first one here, in the translation, we move 0 in the x, but we move down 5 in the y. So we go down 1, 2, 3, 4, 5. And this is A prime. We do that over 0, down 5 for all of our points. I guess that's E and E prime, but I was thinking figure A and figure A prime. So we have figure A and then figure A prime here. And then we want to do, we reflect it across the line x equals 0. We know x equals is a vertical line. This is happening at x equals 0, which is the y-axis. Okay, and then we reflect across. And so we draw a perpendicular line, We count our spaces, one here, one here. There we go. We draw our perpendicular lines, 1, 2, 1, 2. Our new image, draw our perpendicular line, plot this point, and we now have figure B. This is a glide reflection. We could have reflected first and ended up over here in this quadrant and then glided down. Doesn't matter. We use our translation rule and our line of reflection. So don't forget, use your translation rule and your line of reflection. All right. The next problem. So can we keep them on here together? Yeah, that's good enough. Uses the triangle TEX from above. So pause the video, see if you can do this problem. All right, we were given the translation rule, x plus 1, y, and a line of reflection, y equals -2. You can do them in any order. I chose to translate first. I moved all my points +1 in the x direction and 0 in the y direction, so everything just slid to the right 1. And then I reflected across the line y equals -2. So I drew my perpendicular lines, counted my spaces, and you can see that we now have opposite orientation. I could have also reflected first and then just slid it over. I would have ended up in the same spot. Notice this just slid over 1 to the right. Not difficult, but you are going to have to work carefully and probably slow down a little bit. Okay, let's look at our last bit of stuff here. Classifying isometries. So you can map one of two congruent figures in a plane onto the other by a single reflection, translation, rotation, or glide reflection. So we really only have 3 transformations here. The glide reflection, I guess it's kind of a 4th, but it's just a combination of your reflection and translation, right? And actually everybody is just made up of reflections, aren't they? Translation is 2 reflections, parallel lines. Rotation is 2 reflections, intersecting lines, right? All right, there are only 4 isometries. If our orientations are the same, then we either have a translation, which is just a slide, or a rotation, which is a turn. And we know that those go counterclockwise. Okay. If your orientations are opposite, then you either have a reflection, which is just a flip, or a glide reflection, which is a slide and a flip, right? Flip across a line parallel to your translation line. Don't forget that. Don't forget these 2 lines are parallel. Very important. All right, when we classify isometries, we are starting here with our original isometry over here, turn with an arrow. Are the orientations of the pre-image, this is our pre-image over here, this is our original, and image the same or opposite? What type of isometry are you using to map the pre-image to the image? So let's look at A here. Well, what's the first thing we notice? We notice that our orientations are opposite. That means we either have a reflection or a glide reflection. And because it is not just a simple reflection, right? We didn't just flip it over a line of reflection, right? We can't get from our pre-image here and just draw a line and flip it over to here. Okay, that's not possible. So we know that it has to be a glide reflection. Opposite orientation, but is not a reflection, is a glide reflection. So we know we had to use something extra there, which means it's a glide reflection. All right, this one, our orientations are the same. That means we either have a translation or a rotation. So can we just slide our original onto that one? No, there's no way to just slide it. But we could rotate around. That's not counterclockwise. There we go. We could just rotate it around, right, and get it to there. So it's not a translation. We have the same orientation, but not a translation is a rotation. So that's how you figure these out. There's only 4 choices, and they're in 2 categories. You either have the same orientation and opposite orientation, and from there it's pretty easy to figure it out. So go ahead and try to do this last problem at the bottom. Pause your video, and I'll see you soon. Okay, hopefully these were easy to see. It says each figure is an isometry image of the figure at the right. What are the orientation and what type of isometry do we have? So this first one here, we notice we have the same orientation, right? Our P is going the same direction. Well, how could we get it there? If you can imagine this going around in a big circle, right? With some point here kind of in the middle, just like the hands of a clock, okay? We would end up with the same figure. Is that where it would rotate about? These things, it doesn't look quite right. Where would our center of rotation be? Our center of rotation is clear up here somewhere. Look at this, because if we went way up here and came around, think about the bottom part of it. That would be how it was. So this has to be like a really big circle, way up there. Sometimes it's easier for me to think of these in a clockwise direction first and then figure out how to go counterclockwise from there. Because, you know, clockwise is how everything works for us. All right, so anyway, you can see that you can just rotate it around some point way up in there and get to there. All right, how about this next one? B, obviously the same orientation, and all we have to do is slide it over here. That is just a simple translation. We just slid it over. And our last one. These have opposite orientation, but it's not simply just flipping it upside down here, right? So we know that it is more than a simple reflection. That means that it has to be a glide reflection. So we slide it over here, and then we flip it over some line that is parallel to the line of translation. So we translate and we flip, therefore glide reflection. And we know that these 2 lines have to be parallel. Slide it over and flip it. Hopefully you got those answers and can see them. Sometimes these rotations can be a little bit challenging to see and find out where the center of rotation is, but I just look at them like hands of a clock. How would I get that one moving around in a circle to get to the next place? And then that helps me see where the center of rotation would be. All right, well, this is our very last lesson. Compositions of reflections And if you work carefully on these, I know you will do a great job, just like you have done all the way up to here.